Hey everybody, we're back. Mr. Hayes, Mr. Hayes' World of Math. We're reviewing AP Stats. I know I sound like a broken record, but we're almost halfway there. Actually, we are halfway. We've got approximately 3.5% of all children born in a certain region are from multiple births, meaning twins, triplets, etc. Everybody else, and of those children who come from multiple births, 22% are left-handed. Of the children born in the region of single births, only 11% of those are left-handed. So the first question is, what's the probability that a randomly selected child born in the region is left-handed? So this is very similar to the setup of what we did yesterday when we were talking about probability. Just a tree diagram. I've got over here multiple birth or single birth. Multiple births are 0.035, 96.5% for the remainder part. Kick it over here. Are they left-handed? Great, that's a 22% chance. 78% chance not, 11% chance if they're left-handed, and a single birth. So then what we need, since we're looking for a probability of left-handed, is we're just going to follow the tree to the left-handers. So we're going to do this. And as you go, you're going to multiply the different probabilities as you go, add them up at the end, boom, Bob's your uncle, and you have your number. So in this case here, we will end up having this. The top line turns out to be just under 1%, 0.0077. The other one is just over 10, so 0.1062. Add them all up, and we have an 11.3% chance of getting somebody randomly who is of a left-handed person. So if we go down here to part B, what's the probability that a randomly selected child born in the region is a child from a multiple birth, given that the child is left-handed? So you know that the kid who's chosen was left-handed. What's the probability that they were from a multiple birth? So the setup for that one, remember, is this. Now the given focuses in on what we're talking about. So what's the probability that they're a multiple birth if they're given left-handed? So when we do that, if we look back up here, we're only caring about the people who are in these yellow lines. These other people we're not going to worry about. Why? Because we know we picked a left-hander. Those people are right-handed. We're not going to mess with it. So that means that our population is the person who we pick from has a population chance of 11.39%. So instead of being 100%, that is going to be our bottom denominator there. So probability of getting a left-hander, probability of both left-hander and a multiple in the top. So you get this. We have 11.39% as our population, since that's the group that the person is from, and we know that. And then the chances that they were from multiple birth and left-handed is the 0.0077 number. Divide that out, and whoop, there it is. So if you know that you have a left-hander, there is a just under 7% chance that that person also came from a multiple birth. Twins, triplets, quadruplets, etc. And then for part C, a random sample of 20 children are born in the region will be selected. What is the probability that the sample will have at least 3 children who are left-handed? Couple of things. So now we're starting to get into those binomial distributions. So now what you want to think about is that we want to have, what's the probability that we have 3, 4, 5, 6, 7, all the way up to 20? Or another way of saying is, what's the probability that you don't have 0, 1, or 2? And then we take the difference from that, okay? So a couple things to think about. You have your binomial CDF. Now, binomial CDF only covers, so I've got, actually, let me do it for typing. So we've got we could have 0, we could have 1, we could have 2, we could have 3, we could have 4, we could have 5, we could have 6, etc. 19 and 20. Okay. So we want everybody in, we'll do highlighting. We want everybody here. 3 or more. So what's the probability the sample has at least that? Now, when you do binomial CDF, it only goes up from the left. Okay, so this number right here that we're typing into a calculator is only this part. Okay, so that means that whatever that number turns out to be, which in this case here is about 60%, then we need to go through and we're going to subtract that out. Okay, so that means that the probability is right around 60%. So we are going to go through and we're going to do 1 minus point, let's go 5 decimal places, 976. So it's going to be right over 40%. Actually, it's going to be 40.24 or 40.24. And that's going to be the probability. So just be really careful in terms of the setup of that, because again, binomial CDF will only go up until we see what's going on, and then everything else will go from there. Now, when you type this in into your calculator, the first thing here is going to be trials, and then you're going to have your probability. And then the last one is going to be your X value that you're looking for. All right, so those would be how you would label those out. And that's it. So you can see it relies a fair amount on the probability. They just take it a little bit extra from there. Now,